Bismillah Rahman Rahim. Assalamu alaikum. Today, in this video, I am going to show you how stationary waves are formed in a string. Stationary waves formed in a string, and we are also going to discuss a mathematical formula that we would have to memorize in order to solve questions. Okay, so a stationary wave formed in strings. Imagine that I have a rigid surface and another rigid surface. That means I have two fixed surfaces. They're not going to play any role in our discussion here. They're just two surfaces which are holding together a string. Okay, they are holding a string tight in a situation that looks like this. Okay, the length of the string is small l. Okay, and if you pluck the string at the center or anywhere for that instance, if you pluck the string at any position, the string is going to vibrate up and down. The string is going to vibrate up and down, but the string. All right, sorry about that.
Hello, Assalamualaikum.
Yep. Okay, sorry about that. Can you hear me?
Yes.
All right, that's great. I was talking about the string. Wherever you pluck it from, the particles are going to vibrate up and down. But these particles, the ones that are fixed with the rigid surface, they are not going to move. Why? Because they're fixed. So these particles are called nodes. Nodes. So what is a node? A node is a point on a stationary wave. Point on a stationary wave which has permanently zero displacement. Those particles which do not move, they are called nodes. Next, I would like to show that to you on a simulation. Okay, I'd like to show you a simulation about this. I would just let it load. During that time, I will tell you something else as well. Now, a node you would have to define for 1 mark. It is a point on a stationary wave which has permanently zero displacement, and an antinode. We would have to define both of them. Antinode. So by definition, an antinode is going to be a particle a point on a stationary wave, point on a stationary wave which reaches a maximum displacement. Okay, that's the definition for node and antinodes. All right, these are two characteristics of a stationary wave only. No other type of wave has nodes or antinodes forming in it. That means, of course, the other type being progressive waves. Nodes and antinodes are not present on a progressive wave, because in progressive wave, every particle follows the same kind of movement, follows the same kind of pattern, okay, but with a slight delay. But in case of stationary waves, there are some particles which appear to be present on their normal line throughout the movement of the wave. Like, I am going to show you a simulation here for that purpose. Let's see. If I use the oscillate option, The particles vibrate up and down. They get reflected from the fixed surface. And here, a stationary wave is formed. Now, I would like for you to identify this particle here, this particle here, this particle here. These particles are going to stay very close to the normal line. So if it was supposed to be an ideal stationary wave, these particles are not going to go anywhere. But of course, a simulation, it has some imperfections, but you will see that these particles which I have circled, they are going to stay very close to this central line. See, if I let it go frame by frame, you can see these circled particles, they appear to stay at their exact same position or move slightly upwards, okay, upwards or downwards. So such particles, they are called nodes. And if you look at this particle, I'm going to highlight it with a different color, orange, this one, this particle and this particle and this particle. You will see these particles are going to reach positive maximum displacements and negative maximum displacements. I'm going to show you frame by frame. Right now they are present at their, the ones which are present at the negative maximum, they are going to move in the upwards direction this way. And the particle that is already reached the maximum position is going to come downwards to the negative maximum. See, I'm going to play it frame by frame again. You will see these particles, they are all moving downwards together, and particles which are present below, they're all moving upwards together. See, this way. The particle that has reached its negative maximum position, like this position, it has now reached a positive maximum position. And the particle that had reached positive maximum has now reached negative maximum. The negative maximum position has now reached positive maximum. So these points, they are called antinodes, and these points here, which are present close to the normal line, they are almost going to stay at the same position. These are called the nodes. So do you understand what are nodes and antinodes now?
Yes.
Okay, that's great. Moving back to our discussion, here I'm going to make a formula for you as well. But first, when we pluck it at the center, there will be a wave traveling towards right and another wave traveling towards the left. I arbitrarily chose the center. I could have plucked it anywhere. This process will be true for any position on the string. If I pluck the string at the center, pluck means just to disturb it. It doesn't mean to break it. Wherever I pluck the string from, a wave is going to travel towards the right and another wave is going to travel towards the left. And then both these waves, they will get reflected from the boundaries, and then after reflection, they're both going to move towards the center. So you remember the formation of stationary wave. There need to be waves, two waves. They need to be traveling in opposite directions. Both these waves should be of the same type, and both these waves should be traveling in the same medium. Both these waves should be traveling in the same medium. These are the four necessary conditions of the stationary wave to be formed. I will see that there are many particles present on the string, and we will observe all these particles being displaced vertically upwards. And then after some time, all these particles are going to move in the downwards direction as well. All particles move upwards, and after some time, all these particles will move downwards as well. Okay, so the particle that reached the maximum position, this will be an antinode. After some time, the same particle is going to move downwards as well. So we count this particle as antinode. So it's counted only once. You don't count these two A's to be two separate antinodes. Right now, you're able to see two nodes and one antinode. Are you with me so far?
Yes.
All right, that is great. Right now, you can see that one complete crest, or after some time one complete trough will be formed, right? Both of them don't form at the same time. You can see in the simulation where there was a crest, after some time at that position there's going to be a trough, and where there was a trough, after some time there's going to be a crest forming at that position. You can see here there's a crest forming. In this diagram, I'm showing you different wavelength, and the diagram that I showed you in the notes, I am showing you a different wavelength. So don't compare that diagram with this one. I'm just trying to show you that right now there is a crest here. After some time, there's going to be a trough present at this space. And where there was a trough initially, there is going to be a crest forming after some time. Are you with me so far?
Yes.
Okay, that's great. So right now, this length L, inside this length L, half a wavelength is being formed. Half a wavelength is being formed inside that length L. How do we know it's half a wavelength? One complete crest or one complete trough. One complete crest or one complete trough, that comprises of half a wavelength. So from here, lambda becomes equal to 2L. This 2 goes on and gets multiplied with the length L. Are you with me so far?
Yes.
Now, recall the equation V equals to F lambda. Okay, from here, frequency will be equal to V over lambda, and in place of lambda, I want to substitute 2L, where V is going to be the speed of the wave, L is going to be the length of the string, and F is going to be the frequency of the wave that is formed here. Frequency equals to V divided by 2L. Is everything okay so far?
Yes.
Okay, now things are going to get weird. Okay, before that, I'd like to tell you that right now, this frequency is called fundamental frequency. Yeah, or we also call it the first harmonic. This is called the first harmonic. What does that mean? Fundamental frequency or whatever, the first harmonic. That means this instrument, let's call it an instrument, this instrument cannot produce any frequency that you want from this. This instrument cannot produce any frequency of the wave that you want. It will only be able to form specific frequencies. I'm going to show you a different frequency in a few minutes, but right now, this instrument is able to create a specific frequency that is called the first harmonic. If you have ever played a guitar or you know something about it, a guitar cannot produce all frequencies. It can only produce specific frequencies of sound, and those frequencies are called harmonics. Are you with me so far?
Sir, could you repeat this again?
Yes. I said that I'll write this down as a note. Every instrument cannot produce every frequency of sound. Every frequency of sound or wave. Only specific frequencies can be created. For example, if you ask me to create 100 hertz frequency from this instrument, I can't say for sure if 100 hertz can be produced by that instrument or not. I would first have to use the formula F equals to V over 2L place this 100 hertz over here and check if the length of the string is long enough to create that frequency according to this formula. So every instrument, every musical instrument cannot create every frequencies. It can only create specific frequencies, and these frequencies are called harmonics. Harmonics. Do you get that?
Yes.
Okay. So F, the one that I showed you here, this formula is that of a fundamental frequency or the first harmonics. That means this instrument, the smallest frequency that it will be able to create is going to be calculated by this formula. Let's say if I say the fundamental frequency is 100 hertz, this instrument here cannot create a frequency less than 100 or more than 100. It can only create the fundamental frequency to be equal to 100 hertz. That is why if you have ever played a guitar, you would know every string on a guitar, it has a very distinct sound, and people who play guitar, they can hear that sound and tell which string was it, the first or the second or the third or the fourth or the fifth. I think there are 5 strings. Of course, this frequency can change depending on the tension in the string, but tension is not in our syllabus anymore. Okay, we only have to discuss the effect of frequency as a function of length. Are you with me so far?
Yes.
Okay, let's say I have the same instrument again. It has the same rigid surfaces, the same rigid surfaces, the same string in between the rigid surfaces, the same length between them. But now I am going to use a different source to cause vibrations. Let's say I move an electronic vibrator. That electronic vibrator causes the string to vibrate at a different frequency. Do you remember that frequency is inversely proportional to wavelength? If I want to increase the frequency, I would have to decrease the wavelength of the wave. So when I use an electronic vibrator, that's the electronic vibrator. It vibrates the string up and down. Okay, this vibrator has a specific frequency. It's going to vibrate the string at the same amount of frequency. I want to create a frequency greater than the one that I've already discussed. So I would have to reduce the wavelength. That way, we are going to see that instead of one complete loop forming, now there will be two loops forming. If you could look at the diagram earlier here, in the same length, there was only half a wavelength forming. Now in the same length, there is one complete wavelength forming. This is indicating that the wavelength has been reduced. Lambda reduced. See, initially in that length, there was half a wavelength. Now in that same length, there are two halves. That means one complete wavelength. So that means you will see the string vibrating like a bold portion here. And after some time, you'll see the string it will be positioned according to the dotted lines. So there were a lot of particles on the string. When the bold portion was formed, all these particles moved vertically upwards like this. And all these particles moved vertically downwards. After some time, when the dotted wave was formed, their positions got changed. Now it has 3 nodes. This is a node, this is a node, this is a node. And now it has 2 antinodes. This is an antinode, this is an antinode. Of course, this point will also be an antinode, this point will also be an antinode, but we don't count them as two separate antinodes. There are still only 2 antinodes forming in this string. Now, if you could see, the wavelength is going to be equal to the length of the string. Okay, the wavelength is going to be equal to the length of the string. We are interested in the frequency. Now frequency will be equal to V over lambda. I can write, instead of lambda, I can write L. And if I multiply this V with 2, and then I multiply the length L with 2 as well, it's not going to make any change to the equation. Tell me, does that make any difference mathematically?
No.
Absolutely not. But why have I done this? You will be able to appreciate that in a few minutes. Right now, just roll with it. This frequency is going to be called F2, that will be equal to 2V by 2L. Now the same instrument is able to produce another frequency. This frequency will be called second harmonic. The first one was called fundamental frequency or the first harmonic. This one's called the second harmonic. Let's say if the first harmonic was 100 hertz and the second harmonic is 200 hertz. Of course, how did I calculate it? I placed the value of speed of the sound and the length L of the string, and I calculated F2. Let's say the fundamental frequency F1 was 100 and F2 was 200. Now these represent only specific frequencies. That means this instrument won't be able to produce any frequency less than or greater than 100 or less than or greater than 200. That means the first note that this string can produce will be called 100 hertz, will have a frequency of 100 hertz, and the second note that it can produce, that's going to be 200. This instrument will not be able to produce any other frequencies but these two. Then I'm going to show you the third harmonic. In case of third harmonic, the instrument is still going to be the same, but we will be vibrating it by using a different source, a source that has a different frequency. So it will vibrate the string with a different frequency, of course. When I want to increase the frequency, I have to reduce the wavelength, of course. This point had to be a node. This point absolutely had to be a node. But now, in order to create the third harmonic, I need to have 3 crests or troughs. A lot of students like to memorize it in such a way that for the first harmonic, there was only one big loop. For the second harmonic, there were 2 loops. For the third harmonics, there will be 3 loops. Examiner often asks you how many loops are going to be there or how many nodes and antinodes are going to be there. So you should either learn how to draw them, or you should memorize them. Keep this in mind. If I drew this diagram like this is not going to be correct. Why? Because this is a crest that has a smaller length. This is a trough that appears to have a longer length. And then this is another crest that appears to have a longer length. And this one's another shorter one. That's not the right way to draw it. Every crest and every trough should have the same length. That means this length from one node to another node, this has to be equal to half a wavelength. This node and this node, they should appear to be equal to the previous one as well. And this node and this node, the length between them should appear to look like the ones that I have mentioned before. So that means it should be visibly identifiable that nodes and antinodes are all almost equal distances. Just by looking at them, we should be able to identify that. If you want to draw a stationary wave, you absolutely cannot draw a crest to be a bigger and a trough to be a smaller length. I hope that makes sense.
Yeah, it does.
Okay, that's great. Now here, lambda. How many wavelengths are there? There are 3 halves. That makes it 3 by 2 wavelengths that are being formed inside the same string. What is happening? The same string is being used, but we are vibrating it by using different sources that is able to produce different frequencies or different wavelengths. That means we are producing different wavelengths inside the same strings. If we remember, the frequency was equal to v over lambda. Instead of v, we place the value of the speed. Instead of lambda, from here you can see lambda is 2L by 3. So you substitute 2L by 3. This 3 moves on to the numerator side. The third harmonic frequency comes out to be 3V by 2L. That is going to be the frequency of the third harmonic. The third harmonic. That means after the second harmonic, I wanted to create a wave with a larger frequency, with an even larger frequency. So after the second harmonic, the next frequency this instrument will be able to produce is called the third harmonic. So this one's going to be called the third harmonic. Now I'm going to write all three formulas together, and then I'm going to make a general formula for you. F1 was equal to 1V by 2L, F2 was equal to 2V by 2L, and F3 was equal to 3V by 2L. Do you remember that I multiplied the speed with a 2 and the length with a 2 as well? Why? Because the 2 in the numerator, sorry, the 2 in the denominator had to be common with every frequency formula. See, for the first harmonic frequency, there was a 2L at the denominator. For the third harmonic frequency, there was a 2L at the denominator. That is why I multiplied the 2 with the length L in the second harmonic frequency. Now, if I combine all these three formulas, what do we see? The 1V by 2L, V by 2L, V by 2L, V by 2L. This is common for all three formulas. Even the F is also common for the all three formulas. But what's different? The number that is being multiplied with V and the number in the subscript of the frequency. Similarly here, the number in the subscript of the frequency and the number multiplied with the V. The number in the subscript and the number being multiplied with the V. These are same. These are changing, sorry. So I can write the general formula to be equal to Fn into Nv by 2L, where N is equal to 1, 2, 3. It could even be 4, 5, or 6. I showed you only 3 harmonics. I will show you another one if you request me to. But the results are not going to change. The N is indicating the of harmonic number of harmonics. So if you'd like to calculate the frequency of the fourth harmonic, so instead of this N, just place 4 here. The speed of the wave is a constant and the length of the string is also a constant. So it's not going to change at all. So all you have to do is just change the N and you'll be able to find out the frequency of that particular harmonic. Do you understand that?
Yes.
That is great. If you understand that, I'd like to tell you one more thing about this. Fn equals to n times V over 2L. Do you remember that this V by 2L, isn't that the frequency of the first harmonic? Isn't that equal to the frequency of the first harmonic? Of course it is. So I can write the general formula to be Fn equals to n times of F1. That means you can eliminate using constantly changing V and L. V and L are also constant. So you just divide V by 2L. That was the frequency of the first harmonic. You just multiply the number of harmonic that you need and you'll be able to find out the frequency of that particular harmonic. For example, I tell you to find out the frequency of ninth harmonic, and it is given in the question that the first harmonic is equal to 150 hertz. All you have to do is Fn equals to Nf1, if you want to find out the frequency of the ninth harmonic, instead of small n over here, you're going to place 9, and instead of F1, you're going to place 150. That's the frequency of the first harmonic that's supposed to be given in the question. So the ninth harmonic comes out to be equal to 1350 hertz. So this instrument that we are talking about, the first harmonic it will produce will be 150. First harmonic indicates the smallest frequency that it can create. The second harmonic is going to be 300. The third harmonic is going to be 450. The fourth harmonic is going to be 600. The fifth harmonic is going to be 750. What am I doing? I'm just increasing the number of harmonics here instead of n. Keep multiplying it with 150. F6, the sixth harmonic is going to be equal to 900. Okay. The seventh harmonic is going to be equal to 1050. The eighth harmonic is going to be equal to 1200. And the ninth harmonic is going to be equal to 1390. Examiner can ask you to find out any of these harmonics. Okay. So all you have to do is use that general formula that I have taught you so far, this one. Is that all right?
Yes.
Okay. Now I'm going to show you the formation of stationary waves in an air column. In an air column. What is an air column? Of course, an air column is simply going to be a container that is, there will be two types of air columns that we are going to talk about. First is going to be open at both ends, and the other type is going to be open at one end. First, we'll talk about open at one end. Imagine this is a cylinder that is sealed at the other end. Okay, it is sealed at the other end. That means this other end is a rigid surface. And here I have a loudspeaker because I am going to be producing stationary wave in an air column, and inside air we can produce only one wave, and that is the sound wave. So I'm going to use a loudspeaker that I connect with a sound source. Okay, now there are going to be air particles present inside. Of course, air particles are going to be present inside. We know that sound is a sound is a longitudinal wave. Longitudinal wave. What does that mean? The particles of air, they are going to vibrate back and forth. Okay, when a sound wave travels through air, the particles are going to vibrate back and forth, but they are difficult to show in terms of a stationary wave. That is why for the time being we are going to assume, and the examiner will also assume sound wave to be a transverse wave, because it's easier to show stationary waves using a transverse wave rather than longitudinal one. First, we are going to try and develop a concept, and then I'll show you what a stationary wave will look like using longitudinal notations. Right now, there will be different particles here, a lot of particles, air particles. When sound travels through these air particles, sound is going to travel towards the right, then it's going to get reflected from the rigid surface, and then it's going to travel towards the left. So the wave that travels towards right and the wave that travels towards left, they are both going to have same frequency. Why? Because they both come from the same sound source, same frequency, same type, two force, two waves. So that means this situation checks all the necessary boxes, same space. These are the four necessary conditions for stationary waves to be formed. So the situation that I'm describing for you, the air column and this loudspeaker, it checks all the boxes that there will be two waves traveling in opposite direction. This one is just a reflected wave, okay? It's not coming from a different source. It's just a reflected wave. They both are going to have the same frequency because both of them are coming from the same source. They're both going to be same type. Same type means both of them are sound waves. They're going to be two waves and they're going to have to travel in the same space. That means they will absolutely have to interfere with each other. So in such a situation, the particle that will be present at the rigid surface here, the one that I'm showing with red, this red particle is present at the rigid surface. So it's not going to be able to move. That means there will always be a node forming at this point. Because this particle is present at a rigid surface, it won't be able to move back and forth. And this particle here, this particle is present at an empty open space. That means this particle will be able to exhibit maximum displacement constantly. So at the open end, there is always an antinode formed. I'm going to explain why a node is formed here. A node is formed due to a rigid surface. Due to rigid surface, particle cannot vibrate back and forth. Particle cannot vibrate back and forth. Whereas why is an antinode formed over here? Antinode formed as particle is free to vibrate. That means even if we change the wavelength and change the frequency of the wave, there will always be an antinode forming at the open end and a node forming at the close end. Are you with me so far?
Yes.
All right, that is great. Okay, now we are going to perform similar calculations, like the ones that we discussed earlier. Let's see. That's the pipe, or that's the air column. Okay, that's the loudspeaker. Here there will always be a node, and here there'll always be an antinode, either a positively displaced, or a negatively displaced. Now, for the fundamental frequency, the wavelength has to be largest. We remember fundamental frequency is the smallest frequency of a stationary wave that any instrument can create. So in this case, we can see an antinode and a node forming. So this is going to be the first stationary wave that this instrument can create. I would like to recall for you that whenever we represent a stationary wave, this is how we represent it. Okay. I have randomly drawn a little segment of a stationary wave. Here, there will be a node at this position and another node here and another node here and another node here and another node here. I have just drawn a segment without any logic. I could have just drawn till here as well. Doesn't matter. It doesn't matter. I randomly drew it just to show you something. Okay. These points here, this one's an antinode, this one's an antinode, this one's an antinode. All right. So the distance from a node to a node is half a wavelength. The distance from an antinode to an antinode is half a wavelength as well. Okay. The distance from one node and skip another node and another node, reach the next node. So this distance is going to be one complete wavelength. And if you start measuring from an antinode, you skip an antinode at the center and then you reach the third antinode, this distance is going to be one wavelength as well. So you have to keep it in mind that the distance between a node and a node is half a wavelength. So by that logic, the distance between a node and an antinode is lambda by 4. I'm going to write some things down here for you. The distance from a node till a node, this distance is half a wavelength. The distance from a node to an antinode, this distance will be equal to 1/4 of a wavelength, lambda by 4. Then this distance from an antinode to an antinode, this is going to be half a wavelength as well. But if you look at a distance from a node to a node and then another node, this distance is going to be equal to one complete wavelength. And then the distance from an antinode to another antinode and to another antinode, this distance will be equal to one complete wavelength. Are you with me so far?
Yes.
All right, that's great. Now, from here, the
What did you
largest,
write in the last one?
sorry, go ahead. Go ahead.
Antinode to antinode to antinode.
Right. That's where this is where I wrote it. Antinode to another antinode. That's going to be lambda.
Okay.
Okay. Okay. Now, when I was trying to find out the fundamental frequency, I would have to draw the largest wavelength that could be accommodated. Not, we don't have to draw a complete wavelength. We only have to draw a little segment where an antinode and a node are drawn. That comprises of 1/4 of a wavelength. You see, the gap from an antinode to a node, that is going to be equal to 1/4 of a wavelength. Right now in the length L of the column, lambda by 4 wavelength is accommodated. So if I recall the frequency, F1 is going to be V over lambda 1. Instead of lambda, I'm going to place 4L. Why? Because lambda was equal to 4L. So the first frequency, the fundamental frequency that this instrument can create is going to be F1 equals to V divided by 4L. Now that formula is not the same as the one that we discussed earlier. That had V by 2L in it. Why? Because it had nodes present at both the ends. But here there is an antinode and a node. That means initially in that diagram, the previous one where we talked about a string, there was the minimum wavelength that we could accommodate in that instrument was half a wavelength. Sorry, the maximum wavelength that we could accommodate in that length was half a wavelength. Here, the maximum wavelength, the maximum part of a wavelength that we could accommodate in the air column is lambda by 4. Now I want to increase the frequency. I want a bigger frequency to be produced by the same instrument. What am I going to do? This is the instrument, the same instrument. This instrument has the same length L. It has the same rigid surface. It has the same loudspeaker. The same loudspeaker is attached with a sound source. Now, this loudspeaker, I can change the frequency that I am supplying to it. Change frequency or wavelength. If I want to increase the frequency, I would have to reduce the wavelength. But an antinode has to be present here and another node has to be present here. Now, if I want to decrease the wavelength or increase the frequency, I would have to incorporate more nodes and antinodes over here. So initially there was 1/4 of a wavelength. Now, if I draw a node at this point, there would have to be an antinode present between two nodes. That's compulsory. An antinode is always formed between two nodes. So that is going to be the next harmonic that this instrument can create, you can see that the distance between node and antinode, it appears to be approximately same by naked eye. That's, I have drawn that strategically. I couldn't draw a node at any position wherever I want. I can't do that. Nodes have to be strategically positioned so that the gap between an antinode to a node stays the same for wherever a node and an antinode are present. Are you with me?
Yes.
Okay. Now you can see how much of a wavelength is produced in this case. From a node to a node, that's half a wavelength. And from a node to an antinode, that's 1/4 of a wavelength. So 3/4 of a wavelength are being formed inside the length L. So from here, lambda will be equal to 4L by 3. 4L by 3. If we remember, the frequency is going to be V divided by lambda. That leaves me with, instead of lambda, I'm going to place 4L by 3. This 3 has to go in the numerator. So the next frequency that is formed will be equal to 3V by 4L. This is going to be the third harmonic. Now that's weird. Where did the second harmonic go? That's what I want to tell you. Every instrument cannot create every harmonic. The instrument that is closed at one end, it will be able to produce the first harmonic, and the next frequency that it will be able to create, that will be called the third harmonic. Why? Because you look at the general formula. For the first one, it was F1 equals to 1V by 4L. And for the next harmonic, F3, it's going to be 3V by 4L. There will be no second harmonic in this case. No second harmonic. Why? Because even if you look at this diagram, there will always be 1/4 of a wavelength. If I try to add more nodes and antinodes, there will always be this 1/4 of a wavelength that will always result in the frequency being expressed in terms of quarters and not halves. The previous case in which we talked about a string, there was always an increment of half a wavelength. But here, even if you keep increasing wavelength by half a wavelength, there will always be a 1/4 being added to it at the end. That is why the total wavelength will always be either 1/4 of a wavelength or 3/4 of a wavelength or 5/4 of a wavelength. Okay. So I'll show you the next harmonic here as well. Okay. Just so that we are clear. That's the instrument, and that is the gap. That's the length of the instrument. That's the loudspeaker. I can create a different frequency by using the sound generator. Okay. I have changed the frequency, increased the frequency. Here will always be an antinode. Here will always be a node. So if I include two nodes over here, I would have to strategically place them so that wherever there are two nodes, there will always be an antinode in between them. And the wave that will be drawn will always be proportionate now. You can see the gap between a node and an antinode. It's always similar no matter where you measure it. This is going to be lambda by 4. And this is going to be lambda by 2. You can see the lambda by 2 appears to be almost twice that of lambda by 4, right? Similarly, over here as well, that's also going to be lambda by 4, sorry, lambda by 2. So in this case, what is the total wavelength that is formed? 5 by 4 wavelengths are being formed inside the length L. How is it 5 by 4? Lambda by 2 plus lambda by 2 plus lambda by 4. If you calculate the LCM, so the LCM for 2, 2, and 4 is going to be 4. This one, this is going to become 2. This is going to become 2. This is going to become 1. That makes it 5 lambda by 4. So 5 lambda by 4 wavelengths are being formed in the length L. If you remember F equals to V over lambda, F equals to V over lambda, the lambda from here came out to be 4L by 5. So instead of lambda, you substitute 4L over 5. This 5 goes on in the numerator and gives you formula F5 equals to 5V by 2L. Sorry, by 4L, not 2L, my bad. 5V by 4L. So this is going to be the next harmonic that this instrument can create. Actually, the third harmonic is now going to be actually the fifth harmonic. F5 equals to 5V by 4L. There will be no odd harmonics, no even harmonics. There will be odd harmonics wherever you use this instrument. That's going to be the first fundamental frequency. That's going to be the second smallest frequency. That's going to be the third smallest frequency. This instrument cannot create any frequency other than F1, F3, F5. Then later on, we can also construct F7, then F9. The formulas are going to be very easy to predict. For F7, it's going to become 7V by 4L. For F9, it's going to be 9V by 4L. See, the formula stays the same. What is changing? The numerical value right beside the V and the numerical value at the subscript of F. Only these numericals are changing. Okay, so if I'd like to generalize the formula, we can see V by 4L is common for every harmonic frequency. So if I would like to construct a general formula, it will become NV by 4L, where N is equal to 1, 3, 5, 7, 9, and only odd numbers. Whereas in the first case that I discussed for you, where there was a string attached to two rigid surfaces, there were both odd and even harmonics. Both of them were formed, where N could have had even values as well as odd values, 1, 2, 3, 4, 5, 6. But in this case, the one that I have taught you here, N could only have odd values. That means this instrument could create the first harmonic or the third harmonic or the fifth or the seventh or the ninth. But this instrument won't be able to create any even harmonics. Are you with me so far?
Yes.
All right. I'm going to show you an example over here from this question. Examiner often uses a liquid column. Okay, this is a burette or whatever. It has a little tap at its center and it has a liquid that is filled to the brim. That's the liquid in it. Let's call it to be water. Okay, there is a water present inside this tube. Examiner says that we have a tuning fork, a vibrating tuning fork. This tuning fork can vibrate. It's vibrating. A tuning fork is able to produce a sound wave. They say that when this tap is opened, when the tap is open, you need to understand the scenario, because every time this is going to be the same question, every time. And every year you will see this question occurring. Okay. So the tap is closed, the water is going to rush out. When the water rushes out, of course, there's going to be an empty space left in the container. Of course, air is going to continue occupying that empty space. This is going to be air. Do you realize this becomes a little air column, right? Are you with me?
No, I don't get this.
As the water runs out, there will be empty space being created inside the container. Are you with me?
Yes.
Okay, so when there is an empty space, of course, there will be air that is surrounding it. It's going to occupy that empty space.
All right.
Like if you have an empty bottle laying around, that bottle will not be empty because there is no water in there, but still there will be air inside it. Do you understand?
Yeah.
So don't you see that this kind of becomes an air column, right?
Yeah.
So if the water continues to run out of this tube, what happens to the length of the air column? It will continue to increase, of course, as the water runs out. The length of air column continues to increase. That's not the question. I'm just describing a scenario for you so far. Are you with me?
Yes.
Okay, now listen to the wording very carefully. They say, as the water is running out, a loud sound is heard momentarily. Of course, this instrument is creating a sound wave of a frequency f, and it is also creating that same wave of wavelength lambda. Of course, if it has a frequency f and a wavelength of lambda, the wave is going to travel downwards, is going to get reflected from the surface of the water and come back. Do you remember the four characteristics of a stationary wave? It's supposed to be formed by two waves. Both the waves need to be same type. The wave that is traveling towards water is also sound, and the one that's coming back from the surface of water, it's also sound. The waves are of the same type. Also, they are traveling in the same space. That means both the waves are trying to travel in the same air column. Also, they have same wavelength or frequency. The wave that's coming and the wave that's going, both of them, they have the same wavelength and frequency. Yes, you were saying something.
No.
Okay, that's great. Now, as this open surface where the mouth of the tube is present here, because the particles are free to vibrate, there will be an antinode forming. Okay, there will always be an antinode forming, and at the surface of the water there will always be a node forming. The surface of the water kind of behaves like a rigid surface. That means if you let the water run out, after some time, there will be a stationary wave formed in it. We can't see a stationary wave formed. We will be able to hear a louder sound. Whenever a stationary wave is formed, we are able to hear a loud sound. So I'm going to write that down for you. That's an important piece of information. Whenever a stationary wave is formed, a loud sound is heard. That is still not a part of the question. All of this is just a description of a scenario. Examiner will tell this to you in the statement. This is not what the examiner is going to ask you. I'm going to show you what he asks you. As the water continues to run out, there will be another occasion. There will be another occasion where you will be hearing a louder sound again. Why another louder sound? I will show that to you in a minute. There will come a time when water level will reach a position where there will be another antinode formed on it. Sorry, another node formed on it. That means this is where another node is going to be formed. That means when the water was at this level, the one that I'm showing with dotted line, This is where a stationary wave was formed, so a loud sound was heard. And this is where another loud sound was heard when the water reached this position. Why? Because we know that after a node is formed, wherever there will be another node formed, that's when the next loop of a stationary wave is formed. An antinode can never form on the surface of water. That is why an antinode has to form where simply air is present. So this is where the first loud sound was heard. First loud sound, that means this is where the first stationary wave was formed. You will not call it first or second or third harmonics. No, because when we wanted to create different harmonics, that's when we changed the wavelength. But here we are actually changing the length of the air column. This is where the second loud sound is heard. Loud sound. So here we are changing the length. We are changing length of air column and not frequency or wavelength. Now, this is still not a part of question. What do they ask you to solve in the question? They will simply ask you, what is the wavelength? What is the wavelength of the sound? Okay, so I'll show you how you'll be able to find out the wavelength of the sound in this case. They will show you on a diagram. This is where the first loud sound was heard. The length of the air column was, let's say, 15 centimeter. And then they tell you this is where the second loud sound was heard. And they also tell you that's the length of 30 centimeter. Now you have to remember there will be an antinode formed at the surface and a node formed wherever we heard the loud sound. This is where the node was formed. This is where antinodes were formed. So all you have to do is, this will always be the question from this topic. Okay, in MCQs it's such a popular concept that examiner doesn't like to ask about anything else except this. You have to remember that the gap between a node and a node is half a wavelength. In the question it's given that it is equals to 30 centimeter. So node to node the distance is 30 centimeter, so the wavelength comes out to be equal to 60 centimeter. That's an exam style question for you. They tell you the distance where they hear the first loud sound and the second loud sound, and they will always ask you to find out what is the wavelength of the wave. That's how you can find it. Or you can also use the gap between an antinode and a node and an antinode. You could recall that is equal to lambda by 4. In this case, it is equals to 15 centimeter. So from here, the wavelength comes out to be 4 into 15. That gives you 60 centimeter. The same answer can be derived by using node and node or a node and antinode. Do you understand that?
Yes.
That's where we end our lesson for today. Thank you very much for joining me here.